All right, welcome everybody. Today we're going to talk about lesson number 26, and this is also homework number 26. I decided to make the entire worksheet the homework to kind of motivate you to take not only the notes, but obviously also to do the practice problems. So this is an introduction to calculus with the idea of graphical limits. So we've kind of been dancing around this idea of a limit for a couple of chapters now, and really more so than ever here in section 2.6. So really none of the concepts you see here should really be surprising or brand new, but we're going to just kind of formalize the process really in terms of the notation. So before we go ahead and do that, I want you to remember first polynomial end behavior and then rational function end behavior. Just to remind you, so here in chapter 2, sections 2.1 to 2.5 were all about polynomials. Those are those continuous, nice, smooth curves. Then section 2.6 has been all about the rational functions with all the discontinuities, all of the asymptotes, and all of the holes. Once we get to section 2.7, which is next, we're going to go back and look at both of them kind of at the same time, but you do want to make sure that you're kind of compartmentalizing them into the nice smooth curves of the polynomial with the broken graphs of the rational functions. So when it comes to polynomials, remember that the end behaviors are things like up, down, etc. Here's the notation that we would have been using. So as x goes to negative infinity, f of x goes to positive infinity, and as x goes to positive infinity, f of x goes to negative infinity. Really what that is talking about is the fact that the end behavior is up, down, but again, this is kind of the fancier way that I showed you, really leading us more towards the calculus notation. When it comes to rational functions, when you're talking about end behavior, you are, of course, talking about the horizontal asymptote. So again, going back for a second to the polynomial end behavior, remember that that is determined by the sign of the leading coefficient and whether the degree is odd or even. So the fact that this is to the degree of 3 means it's odd. And negative, so odd negative would be up, down. So remember, to determine a polynomial's end behavior, you have to look at the sign of the leading coefficient and the degree. And then when you're trying to find a rational function end behavior, you have to consider the horizontal asymptote or the slant asymptote, as it were. But in this case, you have the same degree. So you would find the coefficients 2 divided by 1. That, of course, is why you have this horizontal asymptote. So in terms of end behavior, as x goes to negative infinity, f of x goes to 2, and as x goes to positive infinity, f of x again goes to 2. So this notation here, again, is leading us towards our limit notation. So hopefully you've kind of been getting comfortable with it along the way, and now we're going to go ahead and formalize the process. So in calculus, when they ask you to find a limit, and again, you probably have heard that word before, what they're asking you is what y value is the graph approaching, even if you don't actually get there as x goes to a certain value. So everything about a limit is what y value is the graph approaching as x goes to some number. And again, you don't actually have to get there in order for the limit to exist, as long as you're approaching it all the way up to getting closer and closer and closer. What we've been talking about in the last section was as you approach x from a certain value, you may or may not be approaching it from a specific side, meaning a left-handed approach versus a right-handed approach. So we've been using the words left and right. We've also been looking at this new notation, but now we kind of have to use it. So anytime you're approaching a value from the left, in this case 2, you're going to say as x goes to 2, and then you're going to put up in the little subscript a little negative. That is always going to mean from the negative side or from the left side. Whereas if you were approaching a value, again, in this case 2 from the right, you're going to put a little positive up in the subscript, which always means a right-handed approach. So if you take a look at the graph underneath here and these little bugs that are crawling, they're just kind of giving you a little description of what actually is happening, whether you're climbing up or climbing down as you approach a particular value. But so to kind of take this new notation and apply it to this graph, what they're talking about here is as x goes to 2, so that's the vertical asymptote here. So they're saying as you approach 2 from the left side, f of x is going to negative infinity. That would be approaching 2 from the left, and you can see the graph is going all the way down, whereas when you're approaching 2 from the right, the graph is going all the way up, which is why you would be going to positive infinity. Now we're talking about the fact that you're going to -2. So again, notice how now it's x going to -2, and you again have that little superscript, which tells you the approaches from the left or the right. So -2 is now over here. And again, they have those little bugs crawling just to kind of make it more clear. As you're approaching -2 from the left, that means you're traveling down this piece, and you can see that the bug would go down to -infinity. Whereas if you were crawling from the right hand, the bug would be going all the way up, which means you'd be going to +infinity. Now, taking a look at the previous two examples, you're having a left-handed approach and a right-handed approach. It is also possible that you will just be asked to tell me what happens as x goes to -2 without the superscript left hand or right hand approach. In terms of a limit, in order for the full limit to exist, meaning the limit at -2, the left and the right side have to be the same. Otherwise, the limit does not exist. And just so you know, we're going to say does not exist. We're going to abbreviate with DNE. So that was kind of just, setting the table, a little bit of the notation, just making sure you understand what it means to approach from the left and the right. So now let's actually get into some examples. So take a look at the example here, 3x squared minus x minus 2 over the following. This is, of course, a rational function. If I was going to graph this, I would do all the same steps that I've been doing for the past couple of weeks. Something that may or may not be important here, you can factor the numerator and denominator. So whether you need to or not for a question like this, we're not sure, but we can do it just in case. So we can factor the numerator as such, and we can factor the denominator as such. So x minus 2 and x plus 4. Notice that there are no common factors, so we don't have any holes in this graph. So from here, again, notice that there are a bunch of values that are kind of already shown for you. So as x goes to -4 from the left, notice that the graph is going all the way up to +infinity. Whereas when you approach x from the right-hand side, the graph is going all the way down, which would be -infinity. Then as you approach 2 from the right-hand side, notice it's going all the way up to infinity, whereas as you approach 2 from the left-hand side, notice that the graph is going down to -infinity. So not only do you need to be able to answer these questions, but you also do need to be able to write them. So taking those 4 statements, and we're now going to turn them into limit notation. So limit notation, you're always going to use the letters LIM to be limit. Then underneath, in a smaller size, you're going to tell me as x goes where, from what side. So I'm taking this statement first and converting it to a limit statement. So the way that I would say that is the limit as x goes to -4 from the left-hand side of f of x. And you always have to take the limit of something. So this is the f of x function. It could have been the g of x function or whatever I decide. And because it's going all the way up, you would say +infinity. Then notice that we took this statement here and converted it to a limit statement. Then I took each of these statements for as you're approaching 2 and turned those into limit statements as well. So using that new limit notation is a little bit new and part of the reason why we're doing this. So now using the graph and making sure we understand this new notation, let's go ahead and answer some other questions. So consider the limit as x goes to -4 and the limit as x goes to 2. So if you go back to the previous step, you have the limit as you approach -4 from the left and from the right. In order for the full limit, meaning there's no superscript, to exist, these two answers as you approach from the left and the right have to be the exact same. In this case, because one is going to +infinity and one is going to -infinity, the limit does not exist, which we would say is DNE. Notice that in the second one, they're again asking you about 2. So you would go back to the 2 and the 2 that we have here, the left-hand approach and the right-hand approach. And because they are not going to the same spot, that means that the limit at 2 does not actually exist. So again, you're always going to use DNE for short. And for the next box, we're going to use, again, it's the same graph, but now we might actually need to use the equation. So again, we have the equation of f of x, both in standard form and factored form, and we might need that to answer some of our questions. So taking a look at the limit, try to get that all on the screen there so we can see it. Okay, good. So the limit as x goes to 1, as x goes to 1 from the left-hand side. So as we take a look at where x equals 1 is, that appears to be here. As we approach from the left-hand side, we're getting closer and closer and closer to the actual value. If you wanted to be certain what that value is, you could find f of 1, which means you're going to plug 1 into this equation. You can see that because 1 is a 0, that's the point 1, 0. So the limit, as you approach 1 from the left-hand side, you're getting closer and closer to that actual y value, which in this case would be 0. Then you're approaching x from the right-hand side, but again, you're getting closer and closer to that actual point, which again means you're going to 0. Unlike the examples here, when you're going to the full limit of 1, if I now compare this left-handed answer with this right-handed answer, because they are in fact the same, I can say the full limit exists at 0. In the next set of problems, the magic value is 0, which means we want to actually know what is the value of the function at 0. That, of course, means we want the y-intercept. So that would be -2 over -8, which would be 1/4. So that means that this dot right here is really 0, 1/4. And again, if you have the equation, you need to use it in order to find the algebraic limit. So notice that that's a y value of 1/4. So as we approach that y-intercept from the left, I think you would agree that it's heading towards the value of 1/4. You would probably concur that as we're going from the right, you're going to go ahead and get the same 1/4. Then because of the fact that these two things are the same, you can say the full limit exists also at 1/4. Finally, we're going to go ahead and do the last row here. So for the last row, notice that you have a couple of different values. You have -2, you have -6, and then you have infinity. The infinity one we can do easily. We don't have to do any calculations for that. So as x goes to infinity, that of course means over here, that means you would be following where the horizontal asymptote is, which definitely is going to be equal to 3. As far as what's happening at -2 and what's happening at -6, you would actually need to know those y values, which again, sometimes you can read from the graph, and sometimes you need to actually plug in the equation to be sure. So if you plug -2 into the equation, you're going to get -1.5. And if you plug -6 into the equation, you're going to get 7. So as you're approaching -2, which again isn't necessarily quantified here. So as you're approaching -2, you can conclude that the graph is going to -1.5. So that will be your answer here to the first question. -6, we can't see it exactly, but we know that it's somewhere here-ish. Because of the fact that there's no breaks or anything to worry about, we can safely conclude that it's going to 7, which means we were able to answer all of these questions. So this first big example here, kind of making sure you can connect the notation to the theory, and then making sure that you can use the equation as needed. We're going to do one more big example together. So go ahead and take a look at the next page. So this is a graph that would not have a nice simple equation. So it's not something that you could find. It's something that would just have to be given to you. So that's definitely something that we want to kind of make a note of here. So there's no equation, which means you have to estimate from the graph only. And the values are pretty, identifiable, so that really shouldn't be an issue. You're going to find each functional value or each limit, and you're going to use undefined or DNE as appropriate. So I didn't write the actual questions. I'm going to have you write them as we go, because I do think it's important. The more you write the notation, the more likely you are to be able to use it correctly. So notice again, this is the graph of f of x, which means that every limit statement that I write is going to be in terms of f of x. So the first thing that I want you to find is I just want you to find f of -2. That's what's called a functional value, which means you're going to look at the graph. You're going to go to x equals -2. And if you go to x equals -2, notice that you look like you have a couple of different options. Hopefully it should make sense that you are going to choose the closed circle. So at x equals -2, you have a clear y value of 3. That's not actually a limit. That's just an evaluation. Another functional value would be, let's say if I said find f of 3, So that means that you would go to x equals 3. And again, it appears as though you have a couple of different options to choose from. Again, logic would dictate that you should choose the closed circle, which means at 3, this graph has a value of -2. So then f of -5, it appears as though there is an asymptote there. You can see that from the left side and from the right side, the graph is going up, up, up. So in question C, if I'm asking you to find f of -5, because it appears as though there's an asymptote there is no actual value, and you're going to call that undefined. So again, you have to be careful to use undefined if it's an f of, and you're only going to use a DNE when it asks you for an actual limit. So let's go ahead and actually find some limits. So in question D, I want you to find the limit as x goes to 5 from the right of f of x. And again, there's a reason why I'm having you write it. It kind of just forces you to get used to the notation. So locate 5. You're doing a right-handed approach, which means you would be approaching 5 here from the right-hand side. Now notice, as you approach, you're getting closer and closer to this open circle. Even though that value is undefined on the x-axis, a limit just means you're getting closer and closer and closer. So what y value are you getting closer and closer to? Well, that would actually be 0. Remember, the value doesn't have to be defined in order for the limit to actually exist. Let's consider the limit as x goes to 5, but this side from a left-handed approach. So you're still using 5 as the magic number. Here you'd be coming from the left side. Again, notice that even though that value is undefined, you're getting closer and closer and closer to 0. So you can go ahead and conclude that that is 0 as well. Then in F, sorry, kind of going out of order here, so you can do whatever works for you. Let's go ahead and say the limit just as x goes to 5. In order to answer the question, just as x goes to 5, you would have to compare the left-handed approach with the right-handed approach. If those two values are the same, then you can conclude that the limit exists, and it's that. Because they're both the same, you can conclude that the limit is 0. Don't get it twisted with if I said to you, what is f of 5? F of 5 is a functional value evaluation. So if you were to go to x equals 5, again, you would have a choice. Should you choose the open circle or the closed circle? And you should always choose the closed circle, which means the actual value at 5 for this graph is equal to -3. So an f of is not the same as a limit, and that's perfectly fine. Couple more. So h, let's say that I want to know the limit as x goes to -infinity of f of x. So -infinity, that would be here. And again, it appears as though there is a horizontal asymptote. That, of course, indicates end behavior. Where does that horizontal asymptote appear to be? Well, to me, it looks like -5. So we would say that that limit was equal to -5. Again, what we know about asymptotes, we're not actually going to get there, but that's fine. Let's do the limit as x goes to 0 of f of x. So if you're being asked as x goes to 0 of f of x, that means you have to consider both the left hand and the right hand approach. So at 0, the graph appears to have a value of 0, 1. In order to find the limit, you would have to consider the left-handed approach and the right-handed approach. If those two sides are going towards the same exact spot, congratulations, the limit exists, and it's whatever the y value is. J, the limit as x goes to 3 from the right of f of x. So go to x equals 3. That's here. If you're doing a right-handed approach, it means you're coming up from this piece here. What y value are you getting closer and closer and closer to, even if you don't actually ever get there? That looks to me like it's 4. I'll just write k up here so that we can see it. So for k, let's say that you're finding the limit as x goes to 3, but from the left-hand side of f of x. So we're still looking here at 3, but now I'm coming from a right-handed approach. So it appears as though my finger is getting closer and closer and closer to a y value of -2. And for the last question, L, let's say that I want to find the limit just as x goes to 3. So if I want to find the limit just as x goes to 3, I would have to look at the limit that I found from the left compared to the limit that I found from the right. Notice how those two things are not equal, which would tell me that the whole limit itself does not exist. So hopefully you found this to be relatively straightforward, relatively simple. I'm going to ask you to now finish up those last 3 questions. So remember, this entire document, including the notes that we just went through, is homework 26. So when you finish trying, you can go and check the answers, but do make sure that you have the entire document, whether you printed it out or did it on a separate sheet, it doesn't matter, but make sure you have that all done when you go to submit your homework. So thanks very much for tuning in, guys. Hope you enjoyed your first official calculus lesson, and we will catch you next time.